Iniziamo con il primo intervento di Alex de Nardin dall'Università degli Studi di Udine. Puoi iniziare, dovresti avere la condivisione dello schermo.
Al momento non ce l'ho. Ah, ok, sto a posto. Ok, good morning everyone. Okay, so you should be able to see my screen now. And today I'm giving a presentation about our paper called the Time Series Classification Approach to Shallow Web Traffic De-anonymization. So basically, the scenario we try to address is the one in which we have access to the traffic of a private network for which we already built a model for each of the users. So the idea is that we want to be able to determine which of those users is generating the network traffic we are currently observing. One important question when considering this type of problem is which data should we use? The first idea, of course, is to use deep packet inspection because it brings the largest amount of data and also the most descriptive one, since it also gives access to the payload of the web traffic we analyze. But there are two main problems with this approach. The first one is privacy, and the second one is the fact that nowadays most of web traffic is encrypted in some way, and so we simply don't have access to this type of data. For this reason, the data we relied on is the one obtainable by shallow packet inspection, so data that is always granted to be unencrypted because it's usually used for routing purposes, such as IP addresses, TCP ports, timestamp path lengths, and so on and so forth. So given this, we try to build our own dataset by sniffing a large private network for a couple hours during a single session, and we were able to connect around 6 million instances belonging to 151 classes. As we can see, though, the first dataset we were able to build is quite unbalanced. On the x-axis, here we have the different users. Each numerical label represents a different user. And on the y-axis, we have the amount of instances belonging to that class. So as we can see, there is one class in particular which is completely dominating the dataset. And this usually is not positive for classification purposes, since it can degrade the model performance. For this reason, we try to build a second dataset by filtering the first one and keeping only the classes that contain an amount of instances between two predefined values. This second dataset is much smaller. It contains only 2 million instances and 90 classes, but it is much more balanced, and we believe it could give better performance when trying to classify, to perform classification on it. Here we have a tabular visualization of the datasets, and as we can see, there is a further division inside the two datasets I already presented. And this division is determined by the presence or not of the destination IP as a feature. The idea behind this decision is that this destination IP is a categorical feature, and for this reason, we need to map it somehow to a numerical value. And the way we did it in this first experiment is quite naive. We basically just mapped each IP address to an arbitrary numerical value, which carries no meaning. And for this reason, we weren't sure this would help our classification process, and we wanted to analyze both ideas, let's say. So as I said before, each class of our dataset represents a different user of the network, and each instance is a sequence of log interactions between the user and the network. The features we used for the training of the model are listed here. Actually, the first one, the MAC address of the user, is the label we use for the classification process, while the remaining one, namely timestamp, destination IP address, packet lengths, and TCP source and destination ports are used as features for the training. The models we used are two. Our main one is a recurrent neural network, a simple one composed by two stacked LSTM layers with a 50% dropout in between them. This in order to avoid the problem of overfitting, since the dataset we used is quite large. And finally, a dense layer to perform the actual classification task. We also built a simple feed-forward network of comparable size to use as a baseline model to which to compare our recurrent neural network in order to see if actually introducing a temporal component in the analysis would bring better results or not. As for the experimental settings we used, we have that all the models were tested on all the different versions of the dataset. And for each of the datasets, we used 60% of the data for training and 40% for testing. The reason behind this large chunk of data used for testing is that we had a lot of data and it didn't compromise the ability of the model to learn. As for the metrics we used, we relied on the classical ones, so accuracy, recall, precision, and depth score. And all of them were, with the exception of accuracy, were obtained by calculating the value of the metric for each class and then macro averaging them in order to achieve a weighted average based on the class size. Finally, the hyperparameters we used were kept, the values for the hyperparameters used were kept consistent across the different models in order to provide a better comparison between the different models. The only exception is the sequence length, because this is the parameter to which we wanted to analyze compared to the model's performance. So to see if there was a correlation between sequence length and model performance. The results we obtained are shown in the following table. And there are a few things we can notice in this table. The first one, which was interesting to us, is that actually there is a performance increase when introducing a temporal type of analysis. For example, we can see that for the reduced dataset, we achieve only a 63% accuracy with the feed-forward network, so no temporal component considered, which jumps up to almost 91% when we introduce the temporal component, even for a small time window of just of size just 5. So we have a 27% increase in accuracy by introducing the temporal component, which further increases as we increase the sequence length, going as high as 97% accuracy with the largest model. And this behavior, we can see this behavior for all the different data sets and for all the different metrics we used, although in different, let's say, with a different relevance between the different metrics we used. Other interesting aspects regard the introduction of the destination IP as a feature. We can see once again for the reduced dataset that, just to clarify, the reduced dataset is the one that uses the destination IP as a feature, and the reduced no-dest is the one that which doesn't use the destination IP as a feature. And we can see that between the two there is around a 10% gap for all the metrics, which is quite a large gap in performance, and we didn't expect the models to be so different in performance with such a naive implementation of the destination IP. And once again, we can see a similar behavior also for the full dataset, in which the gap is even larger, going from 15 to 50% depending on the metric. One last thing I wanted to point out is that while the best accuracy performance is achieved on the full data set, for all the other metrics, the best values are achieved on the reduced dataset. The reason behind this is that when using the full dataset, which is highly unbalanced, the model tends to over-specialize on the dominating class while achieving worse performance on the other classes. And while on the reduced dataset, the model has a much more consistent performance. Here we can see more visually the performance increase when a temporal component is introduced. We can see that when we go from no temporal component to a small temporal component, we have a huge jump in performance of the models, which then gradually increases as the sequence length gets larger. So to conclude, we believe that we were able to show that performing a temporal type of analysis for web traffic de-anonymization was, we believe that we were able to show that performing a temporal type of analysis was a good idea in the context of web traffic de-anonymization. And even though it's just a first step, we think we made it in the right direction, and we hope it would encourage further research in this area. Of course, there are some points we would like to address in future work. And the first one is that it regards the dataset, because while it was reasonably large heterogeneity, the problem is that we collected all the data over a single session spanning over just a few hours, and we would like to collect more varied data, maybe collected over more multiple shorter sessions. Another point we would like to address is to explore different architectures. In particular, one that we notice is quite prominent in recent research in time series classification is the combination between LSTM and CNN layers, which was able to give good results in this area. And finally, we would like to provide a better representation for the IP address, maybe by providing a better embedding for it. So that was it for my presentation. Thanks for the attention.
Thank you very much, Alex. And so I'm sorry for, I apologize for the delay at the beginning. So I had problem in joining the session, but now I'm here. So is there any question from the audience? So I have, since I don't see any, so I have a question actually. So you show your approach on network traffic. So do you think that can be ported to analyze traffic at the application layer? That would be also, I think, an interesting setting.
Actually, there are different work on that type of problem, and actually is probably the more explored area in this type of setting. So for time series classification, while we decided to go for this to try a different problem, because we have seen that it wasn't explored as much. So we wanted to provide a different point of view, let's say, on a similar problem. But there is also work on that topic.
Okay. Thank you very much, Alex. So let's move to the next presentation. That the paper is titled "Exploiting the Blockchain to Guarantee GDPR Compliance While Consents Evolve Over Data Owners' Control." So the author are Massimiliano, Calani, Giovanni, Denaro, and Alberto Leporati, and the speaker is Giovanni Denaro.
So thank you. Can you hear me?
Yes, loud and clear.
Okay. So let me move one. Okay, so thank you for the introduction. It's Giovanni Denaro from University of Milano Bicocca. I'm going to present you a joint work with my colleague Massimiliano Calani and Alberto Leporati. And as you can see on the title, the work has something to do with GDPR compliance. So let me start by introducing that GDPR is the European General Data Protection Regulation, which started in 2018, and which commits companies to protect the privacy of the personal data of the user that they ask for executing their services. And personal data may include simple identifiers like names, but also sensitive information like age, religion, pictures, or also geolocalization information, medical records, and so on and so forth. And companies that do not comply with the rules of GDPR risk high fines. So for the presentation today, I will focus on what GDPR says about the article that you see here in the slide about the need for the companies to obtain the consent of the users when they want to use some personal data. And they also need to let the user the right to rectify or even revoke their consents at any time without any undue delay on the side of the company. And at the state of the practice, this brings in relevant challenges unaddressed. Because, I mean, it's not straightforward how to, let the user this control to achieve rectifications when they want. And also it's not obvious how companies can promptly react when there is some change in the status of the consent. I mean, for services that maybe are offered in fully electronic fashion, like can be for some web application, that can be done with, ad hoc functionalities in the application. But if we think of the common cyber-physical scenario of many services that are, partially handled by people, they require using multiple applications for executing the service. They maybe use local files to store information, local databases, Excel sheets. The situation becomes more tricky, and it's actually difficult to accomplish this type of control. And what we propose for addressing these challenges is to exploit the blockchain to achieve decentralized handling of the consent. So today I don't have the time to go into the details of how a blockchain technology works. But for the presentation, let me just say that the blockchain works like a decentralized storage, which is organized like a ledger to which we can add transactions, and it runs a consensus protocol such that when a transaction is on the blockchain, it's actually visible for all the peers that are connected in the network and cannot be changed anymore. So, we use the technology because it can provide the decentralized point in which user can store consents, and they can have autonomous control on those consents. At the same time, the companies can adapt to what they read in the blockchain in publish subscribe style. And I will show you how in a while. But before that, let me acknowledge that we are not the first to propose to store consent in the blockchain, and we share with previous work that the personal data must not be directly stored in the blockchain, because if we do that, they cannot be changed, they cannot be deleted anymore, and this is against the rule of GDPR. So we prefer to store in the blockchain only hash codes of the data, just to link the consent to the data to which they refer. But what is new in our approach is that we care about the complete confidentiality of all the information about the consent, because we believe that everything that is on the blockchain can be accessed by all the actors. So it's not we think acceptable that all peers see which consent is granted to which company at any time. So with this in mind, let me go into the details of the solution that we propose. And let me start with showing the format that we use to store the consent in the blockchain. We call it a consent record. And as you see here, it is actually a set of fully encrypted information. So we have the main information about the consent here that are encrypted with a session key that we randomly choose for each record. And the session key itself is encrypted in the record in two copies, with the public key of the company and with the public key of the data owner. So with this record, everybody who can get in touch with the consent record out of the blockchain just sees a bunch of encrypted strings, and only the owners of the private keys, so the company and the data owner, can decrypt the record. And the information in the record codifies, encodes the consent by including identifiers of the parties and the, as I said, the hash code of the personal data to link the consent to the personal data, and also the hash code of the contract that defines the purpose of processing. Then in the record, we have a unique identifier of the consent, the timestamp of the record, and also a sequence number that I'm going to explain in the next slide. But before that, let me say that the whole record is, the integrity of the record is protected by a signature of the data owner that, guarantees that all data in the record are as the data owner actually set. And, as I said, the sequence number is about rectification. So if we want to produce a rectification of a consent, we have to post in the blockchain a new record in which there will be some, new hash code, because it's actually, there is a change either in the personal data or the processing purpose. But then the record will have the same identifier as the previous record, a later timestamp, and a sequence number incremented by 1. So it's actually chained to the previous one. And the idea is that the most recent record that we find in the blockchain must be interpreted as the latest status of the consent. So while the status of the consent evolve, the first record will have sequence number 0, the first rectification will have sequence number 1, then the second rectification sequence number 2, and so forth and so on. And at some point there is a rectification in which the hash code of the purpose of processing is set to the special value 0. We interpret that as a revocation of the consent. And, storing the record in this format brings in important properties, in the sense that this actually prevents any man-in-the-middle attack, because, the records can be decrypted only by the interested parties. Probably both parties see the same status of the consent, so they cannot actually repudiate which is the current status of a consent at any given point in time. And there can be no reflection attack, because if somebody tried to reply the same record again in the blockchain, it will have the same sequence number of a previous record, so it can be simply ignored in interpreting the valid chain of record for a consent. So now, with this in mind, with this format of the record, let me also discuss the interactions that actually happen according to our solution for handling consents. So when a data owner grants a new consent, the interactions simply amount to receiving a request from a company and then producing a new electronic record for the consent and storing it in the blockchain. At that point, the company will, it's connected to the blockchain as a peer, can read the consent from the data owner. And similar to this, to provide rectifications, the data owner can just add new record properly chained to the original consent with the correct sequence numbers and other information consistent. So at some point you can also add a revocation by setting, as I showed, the hash code of the processing to 0. And on the side of the company, our solution settles an application that we call the compliance broker. The compliance broker polls the blockchain regularly, and so at every polling, it actually sees the new records that were posted on the blockchain, decrypts the record that belong to the company, that can be decrypted with the public key of the company, and based on the information, it forms an inventory of the latest status of the consents granted to the company. And with this artifact, it communicates with the services in publish subscribe style. So each service that is interested in a given consent subscribes with the compliance broker. And at that point, when there is a change of status, get from the blockchain, the broker can notify the new status of the consent to the relevant services. And this architecture also requires that the services are actually designed with to be able to react. In the paper we discuss some possible design patterns that can be considered for that. I won't discuss that in the presentation today, so I will refer you to the paper for that description. Let me say that the notification can be both in the form of a call to a service endpoint, an API for services that are in electronic fashion, but it could be also an email sent to some designated responsible people for services that are partially driven by humans.
Excuse me, Giovanni, we are running out of time. So.
Yeah, I'm at the end. So this concludes the presentation. And just I recap, I showed you a solution for handling consent on the blockchain, which allowed data owners to operate autonomously on the consent, and company can react to what they see as change in the blockchain. And what is in the blockchain certifies the status of the consent at a given point of time. And also the distinctive feature of our solution is to keep all the information about the consent confidentially. This is basically work in progress. Up to now, we have a prototype built on a sandbox blockchain, and we aim to build a product based on a permission blockchain where we don't have the problem of the user have to pay fees for the transaction. And we also in the next future aim to run case studies. So this concludes my presentation. Sorry for being a little late. I'm ready if you have any questions. Thank you.
Thank you, Giovanni. So I have a quick question for you. And so when in the last slide you mentioned the permission in the blockchain, can you elaborate on this?
Yes. So a permission blockchain differs from unpermissioned one because it's the consensus protocol is operated by a consortium of authorities. So while in a trusted blockchain we need miners like the blockchain for cryptocurrencies. In the permission blockchain, there is some trust in the authorities that run the blockchain.
That's clear. So the point is, what are the differences in this context? Yeah.
Thank you. The main difference for us is that if we run our solution in an unpermissioned blockchain, the users are can autonomously handle their consents by producing transactions on the blockchain, but for that they have to pay fees. And I mean, that's somehow against the principle that they can autonomously operate, because I mean, it's a cost for them. On a permission blockchain, we envision that there could be a consortium of companies interested in this technology that can run the permission blockchain, and at that point the user can post the request for change of a consent without paying any fee, and that can be actually beneficial.
Okay, thank you very much, Giovanni, for your presentation. So we can then move to the next paper, whose title is Reviewing GDPR-compliant Privacy Design Strategies by Marco Saltarella, Giuseppe Desolda, and Rosa Lanzilotti. The speaker is Marco Saltarella. So please, Marco.
The slides?
Yes,
okay.
you see the slide. Yes.
Okay, so good morning all. Today I'll present our paper reviewing GDPR-compliant privacy design strategies. I'm Marco Saltarella, PhD student at the Department of Computer Science of University of Bari Aldo Moro. I'm also working with FinCon's SPA in the research of development team Bari. So my main research topic is usable privacy. And in my research, we are focusing on the GDPR, the European Union General Data Protection Regulation. And specifically, we are looking at Article 25, which states that the data controller shall implement technical and organizational measures by following the privacy by design and privacy by default paradigm in order to be compliant with the GDPR. So although the GDPR is seen as a step towards the user-centric approach, a problem still remains, which is a usability problem. So as you may well know, in the security field, the user has always been the weakest link in the chain. And so users' behavior while interacting with the system may have security implication, may have bad security implication. So starting from this idea, we can say that for sure the GDPR is the regulation with the most extensive right for its user with respect to other regulation all over the world. However, privacy was discussed well before the GDPR came into effectiveness in May 2018. And for sure, one of the most influential paper on privacy is 7 Foundational Principles of Privacy by Design by Jan Cavoukian, in which she defines these 7 principles that you can see here in the figure on the left. So I'm not going through all of them, but you can see that basically, in some way or another, each of these 7 principles can be found in the GDPR. So the GDPR was influenced by this work. And another work of our interest is Privacy Design Strategies by Hopman, in which he defines 8 different privacy design strategies that you can see in the figure on the right. So we have separate, abstract, hide, and minimize, which are so-called data-oriented privacy design strategies. And then we have demonstrate, enforce, control, and inform, which are instead process-oriented privacy design strategies. So our work is a systematic literature review that basically wants to answer this main research question: how to make effective the privacy by design and privacy by default paradigms during the design and development of GDPR compliant software. So of course, the idea is to survey the literature in order to highlight any gaps to fill with our future works. And so we define a rigorous research protocol, which was based on Kitchenham works. And we define a research query, which was input of 5 different digital libraries. And we retrieved more than 500 papers that then were selected in 3 phases by applying the inclusion and exclusion criteria you can see here. And so what we did is that basically at the end of the process, we selected 90 papers, around 90 papers. And from these 90 papers, we extracted all the best practice, all the advices, all the guidelines we could found, and we categorized them under 8 different privacy design strategy we saw before. So one of the main results is that developers are not prepared to deal with privacy requirements and the lack of tools, and I would say also methods, to translate those requirements into software. And I'm pretty sure that if you have worked in the software development field, you can agree with this statement. So developers are not ready, do not have the know-how to translate the regulation requirements into software requirements, basically. So under the demonstrate strategy, which means that you have to prove that you are implementing the right technical and organizational measures in order to comply with the regulation, the data protection impact assessment is well suggested. So although for the GDPR, the data protection impact assessment is only mandatory when the data processing implies an high risk for the data subject involved. Actually, we found in literature that data protection impact assessment should be done in any case, because it's of course a powerful self-assessment tool. Then we can move to the control strategy. The control strategy means basically that users should always be given the opportunity to express their rights, and this should be implemented in a way that minimize fatigue, while maximizing instead the likelihood that the user make the appropriate decision. And this can be, for example, enabled by, I don't know, a privacy dashboard, for example. And moreover, service providers should move away from a take it or leave it approach and provide the users the right balance between functionality and privacy, which means that the user should be able to select which data he wants to share, and so enable or disable the service features accordingly to what data he wants to share. And also, consent must be separated from the choice of enabling other service-related feature, because, for example, there might be service features which do not require any data collection. So this must be clear to the user that and must be separated from the choice of sharing and the process of informed consent of sharing data with the third-party service. So then we have the informed strategy, and you should always explain in a detailed but understandable and concise way the personal data process. So users should be informed on what data is being collected, for what, and for how long they will be stored. And this can be, for example, supported by using visual reminders. Moving into instead the data-oriented privacy design strategy, we have the minimize strategy. So we have to reduce the amount of data collected and processed to the minimum possible, and this should be decided on a case-by-case basis. So minimize means also that we should reduce the storage retention, and this helps also in reducing the impact of data breaches. Impact of data breaches that can also be reduced by adopting, for example, separate strategies, like, for example, dividing users' data into sub-profiles in order to, for example, avoid account-wide data breaches. Finally, we have the last two strategies, which are hide and abstract. There are many solutions discussed under these two strategies. We have, for example, homomorphic encryption, which allows to do some computation over encrypted data. We have K anonymity, L diversity, T closeness, and we also have differential privacy, which allows you to perform some query on a database, some privacy preserving queries on a database. Then we have encryption, which is suggested not only for transfer, of course, but also for storing data. So data should be stored encrypted. And one technique that is very well suggested is attribute-based encryption, which basically allows you to provide not only confidentiality, of course, being an encryption mechanism, but also access control in the same technique in a scalable way and without the need of setting up a complex security infrastructure. So under the abstract strategy, then we have, of course, data aggregation over time and all the anonymization and pseudo-anonymization techniques. So concluding, in any case, we saw that, I mean, it's worth highlighting that educating the development team, but also as well as the end user, is probably the most crucial way to make these 8 different privacy design strategies work in practice. We saw that many different solutions actually exist to effectively support the GDPR requirements implementation on different levels, but however, still a lot has to be done to make these tools and methods more user-centric. As a result, since the development of security features has often overlooked the principle of usability and human-computer interaction in general, a future goal of this work is to propose a technical and methodological framework to support the user-centric design of GDPR-compliant software. So that's it from my side. Thank you for your attention.
Thank you, Marco. So actually, with the last point remark, you spoiled my question, because I was exactly asking myself whether this was an instance of a more general problem of designing usable or human-centric application, and it seems that you already addressed, I mean, consider this point. So thank you very much for your presentation.
Can I ask a question?
Or sure, please. I didn't see it. Okay, thanks. Go ahead.
No problem. So if we consider, out of curiosity, because you made this review of the literature, if we consider also the right to be forgotten, I mean, when the user wants to delete their personal data and company must comply. So is there any clear solution for services that, or applications that may break their integrity when they delete some data? I mean, because deleting a data sometimes is simple, but if the functionality depends on the data for some integrity constraints, it can be difficult to do.
I mean, I'm not sure about that in what we found in literature, but I have to say that I found during this review that common erasure methods are not enough to comply with the right to erasure. So you have to perform deep erasure using non-specific techniques to actually erase your user data. So that's what I found.
Okay, thank you, Marcos. So, and we are now at our last presentation for this session. The title of the paper is Identifying Anomalous Places and Routes by GPS Feature, a System for Child Monitoring, by Giacomo Battista, Donato Impedovo, Giuseppe Pirlo, Lucia Sarcinella, and Nicola Stigliano. The speaker is Giacomo Battista.
Bully Buster project. Our system was born from the idea of contrast the phenomenon of bullying and cyberbullying, but we are all familiar with the term bullying, but least of all the term cyberbullying. A possible definition of cyberbullying is bullying perpetrated through the use of technologies, for example, smartphones. Therefore, similar situation in technological contexts such as humiliation, offense, and discrimination on social networks are added to previous bullying actions. We took a possible solution, and our goal is supporting parents in monitoring and detection this phenomenon, and how we can do this with the support of a creation of a platform that acquires data from the user's smartphone. So in particular, in this presentation, I present a first function of this platform, which through the data acquired by the GPS, we can able to identify any anomalous path. In particular, the use case in example is which a victim of bullying, in particular a student, on the way home school is forced to change path due to some bully's action. Reading this, a possible question could be, what is the difference between this solution and the solution already on the market? But there is a substantial difference, because actually the current solution allows real-time monitoring on request, or for example a history of the position that the parent must go on to manually check if necessary. This means that which can happen if the parent is already aware of this bullying phenomenon. While in our solution we automate these checks, reporting to the parent any abnormal path. So this means that lets the parent discover this phenomenon. Okay, to do this is necessary to acquire data. Therefore, we developed an app called Shield App. After the installation, the application begins to acquire the GPS data for the smartphone only after the acceptance of the security policies shown to the user, compliant with GDPR. A first part of the policy is shown on the left. In particular, the data acquired are the smartphone IDs, the type of data, in this case sensor of GPS, the value of GPS parameters, so the latitude and longitude, and finally the timestamp and data of acquisition. Once these parameters have been acquired, it is necessary to analyze them to identify the anomaly path or usual path. We use the clustering analysis, and we create from the acquired GPS data the several clusters that are usual path. So all the other values are considered anomalous. We chosen in the first part, in the first time, DB scan, mainly because it allows you to not enter the number of clusters in advance, and this is an essential feature to simulate a real scenario where the number of usual places is not known a priori, because, for example, I can have two usual paths or three, and so on. Once the different paths have been identified, there is the question of how to show them to the user. And to do this, folio map was used. And thanks to folio map, we create 4 interactive maps, maps 1 and map 2, containing all the cluster and outlier of the week. And in this map, it will be possible to view all the cluster or outlier in the form of if map, with the addition of a marker on the position where there are more concentration of data. On the left, there is an example of common path identified, while on the right, there is an example of anomalous path. This marker will be clickable, and we give to the user the possibility to see the city, the postcode, the street, and possible also the name of the place, for example, a school or the home. Here is shown an example of the marker. For the map 3 and 4, we have a two interactive map containing all the cluster and outlayer of the week or of one specific date sorted by time. So in this map, the points are always displayed in the form of if map, but it will contain a slider in which the user, in this case the parent, can move according to the time and the view to precise instant in time with the precise point where the position was registered. Therefore, there are main differences, and the main difference lies in the fact that in the first two cases, two maps, the maps were statics with the data of the entire week, while in the last, the visualization takes place over the time. Okay, what has been described up to now is the functioning of the system. Now we are going to describe the action concerning the experimentation phase. To acquire data, 9 people of different age and sex were chosen, and then we have to install the Shield app and keep the GPS active for 10 days in order to record their movements. The evaluation takes place in two ways, through cluster evaluation metrics and through the questionnaire sent to the user. For evaluation metrics chosen to evaluate with the silhouette coefficient, while for the questionnaire, all users were asked 9 questions of different nature, where in particular question 5 and 6 to calculate an accuracy of the system. Here it is possible to observe an example of question 5 made to the user, where one or more images of his usual path are shown to him. Of course, the image shown to the user were represented the result of the system for that particular user. Okay, now let's observe the result obtained. And for the silhouette score, we observe how, depending on the user, we have values ranging from 0.73 to 0.98, with an average value of 0.91. For the questionnaire, the question will be multiple choice. And for multiple choice question, there will be 5 possible answers with their score. So, for example, strongly agree has a score of 100, agree of 75, and so on. Of all the questions in the questionnaire, only question 5 and 6 were selected for the accuracy calculation. And as they are the most discriminant for the evaluation of the identification of the usual and anomalous path. And we can view that for the question 5, the usual path, we obtain an average value of 91.6%. For question 6, anomalous path, we obtain an average value of 83.3%. With an average value in the total of 87.5%. Given the result, we get observation and the conclusion, both from the silhouette score and from the questionnaire. It emerges how the system is able to correctly identify the usual and anomalous path. That is the goal of the work. But of course, it is important to extend the experiment to more users in order to confirm these results and possible on students who attend to school in the presence. And this is currently not possible due to COVID-19. And finally, the GPS parameters alone are not sufficient to safely confirm a phenomenon of bullying. In fact, for the aforementioned platform, work is underway that also exploit other sensors, social network, text for support a GPS parameter. Okay, thanks for your attention.
Thank you. Thank you, Giacomo. So, is there any question? So apparently not. So I think that the presentation was very clear. So so a question concerning the additional sensors that you would consider to get additional information besides the positioning by GPS.
We consider that the main project is create a platform with among all the several features like GPS support the parents. So we in the first function is GPS parameters, but we are work in progress with sensor, for example, accelerometer sensors, or for example the use of the text in the several social networks. So deleting a phrase or particular word that containing offense, diciamo, particular word in,
yeah. I've lost you now, but I think that your answer was
no, yes, yes, it is the answer.
Okay, thank you. Okay, so thank you very much, Giacomo, for your presentation, and thank you all for all of the speakers for their presentation as well, and the attendees for the participation. Okay, so the session ends here. Thank you very much.